A coil of wire of radius r has 600 turns and a self-inductance of 108 millihenry. The self-inductance of a similar coil of 500 turns will be. So here we need to find the self-inductance, which is the options are 25 mH, 7.5 mH, 50 mH or 75 millihenry. So here the self-inductance is directly proportional to the square of the number of turns of the coil. That is, we have given two conditions where the self-inductance is 108, the numbers of coils are 680 or 600 turns. Next time we need to find the self-inductance when the number of turns are 500. So we take a ratio of L1 upon L2, self-inductance of first self-inductance upon the second when the number of turns of coil first upon the second. So we cross multiply the equation for the in order to get the second self-inductance, and then L1 goes up and N2 square upon N1 square, substituting the values where L1 is 108, N2 is 500 square, that becomes 500 into 500 upon N1 square, that is 600 into 600. The total answer comes out to be 75 millihenry. So option 4 is the correct option. We have the next question. A coil of cross-sectional area 100 cm square is placed in a magnetic field which changes to 4 into 10 raised to minus 2 Weber per centimeter square within 5 seconds. What will be the current across that 5 ohm resistance? So the current is given to be 0.016 amps, 1.6 amp, 0.16 amp or 16 amps. So here we need to find the current, for which the formula is E upon R, which is equals to NA upon the change in the magnetic field upon time upon R. Okay, where N will be the number of turns of coil, here we are taking it as 1. A is the area of cross section, that is 100 centimeter square, so that becomes 100 into 10 raised to minus 4, is placed in a magnetic field which changes to 4 into 10 raised to minus 2 Weber per centimeter square. We are taking entirely into the SI units, so 4 into 10 raised to, that becomes 2. Next in that is the magnetic field area, and then we are going to the resistance, that is resistance is 5 ohms multiplied by the time, that is 5 seconds. So we get the answer to be 0.16 amperes. Okay, so the second option 0.16 ampere is the correct option. So the next question is, a rectangular coil of 20 turns and area of cross section 25 centimeters square has a resistance of 100 ohms. If a magnetic field which is perpendicular to the plane of the coil changes at a rate of 1000 Teslas per second, then the current in the coil will be 50 amps, 1 amps, 5 amps or 0.5 amps. Okay, so here the things which are given is N, which is equals to 20 turns, then the area which is 25 centimeters square, that will be into meters square, that will be 25 into 10 to the power minus 4, and a resistance of about 100 ohms. Then the magnetic field B, which is about 1000 Teslas, and then we need to find the current. So current I will be equals to E upon R, where E will be the number of turns of coils which are changing with numbers of turns of coils upon area multiplied by the divided by the resistance. Okay, and that too with a change in the magnetic field with respect to the time. So your formula becomes Na upon R into dB upon dt, where N is the number of turns, 20 into your area of cross section is 25 into 10 raised to minus 4 multiplied by the magnetic field, which is 1000 Teslas per second. So that will be again R, the resistance R is given to be 100. On solving all this, you get a value of 50 into 10 raised to minus 2, which is about 0.5 amps of current. So the correct option is D, 0.5 amps of current. The next question is, the frequency of AC mains in India is, the current the alternating current mains in India used at the frequency of about 50 Hz. Okay, so we have the options 30 Hz, 60 Hz, 50 Hz or 120 Hz. The correct option is 2, it is 50 Hz. Which of the following conversion is incorrect? 1 curie is equals to 3.7 into 10 raised to 10 per second. 1 bar is 10 raised to minus 25 meters square. 1 quintal is 100 kgs, or 1 liter is 10 raised to minus 3 meter cube. Okay, so 1 curie is yes, it is 3.7 into 10 raised to 10 per second. 1 bar is equals to 10 raised to minus 25 meters square. Yes, but 1 quintal is 100 kgs and 1 liter is 10 to the power minus 3 meter cube. But 1 bar is equals to 10 raised is equals to 100 femtometers square, because 1 femtometer we have, it is equals to 10 raised to minus 15 meters. Okay, so Here, one barn is equals to 100 centimeters square. That will be equals to about 10 raised to minus 28 meters square. Okay, that is the amount for one barn. So here they have given 10 raised to minus 25 meters square, which is wrong. So the second option is the correct option. So next question, the ratio of the volume of an atom or to the volume of a nucleus is of the order 10 raised to 10, 10 raised to 15, 10 raised to 20 or 10 raised to 25. So we need to find the ratio of volume of the atom to the volume of the nucleus. So first we'll write the volume of a atom of an atom, which is equals to 4 upon 3 pi radius of an atom cube, that is 4 upon 3 pi, and the radius of an atom is a 1 Armstrong, that is 10 raised to minus 10 meters cube. Okay, next the volume of a nucleus. Okay, nucleus, which is equals to again 4 upon 3 pi radius of a nucleus cube, that is again 4 upon 3 pi radius of a nucleus is 1 Fermi, that is about 10 raised to minus 15 meters the whole cube. Now we take the ratio of both of them, that gives you 10 raised to minus 10 the whole cube upon 10 raised to minus 15 the whole cube. The rest all things gets cancelled, that comes out to be 10 raised to minus 13 upon 10 raised to minus 45. Okay, which is 10 raised to 15. So the ratio of the volume of the atom to the volume of the nucleus is about 10 raised to 15. The correct option is B. Okay, the astronomical unit is the distance between the earth and the sun, and that one astronomical unit is equal to 1.496 into 10 raised to 8 kilometers, 9.46 into 10 raised to 12 kilometers, 3.084 into 10 raised to 13 kilometers, or 4.596 into 10 raised to 15 kilometers. So basically one astronomical unit is equals to 1.496 into 10 raised to 11 kilometers. Okay, no, 11 meters, sorry, it is 11 meters, and converting into kilometers we get 1.496 into 10 raised to 8 kilometers. So first A is the correct option, that is one astronomical unit is equals to 1.496 into 10 raised to 8 kilometers. The next question, if a coil of 40 tons and area for 4 centimeters square is suddenly removed from a magnetic field, it is observed that the charge of 2 into 10 raised to minus 4 coulomb flows into the coil. If the resistance of the coil is 80 ohms, then the magnetic flux and the density in Weber per meter square inverse is. So basically what we have given here is the N, which is equals to 40 tons. Okay, next thing which is given is the area, which is 4 centimeters square, that becomes 4 into 10 to minus 4 meters square. Okay, next it is removed from a magnetic field, and it has been observed that the charge is Q, which is equals to 2 into 10 raised to minus 4 coulomb, and it flows in the coil if the resistance of the coil R is equals to 80 ohms. Okay, then we need to find the magnetic flux associated with it. Okay, so magnetic flux with respect to the charge, we have the formula, that is the charge is equals to change in the magnetic flux upon R, where change in the magnetic flux is equals to NAB upon R. So the magnetic flux B becomes equals to Q into R upon N into A. Okay, so applying the values, where your Q becomes equals to 2 into 10 raised to minus 4 into your R, which is 80 ohms, upon the number of turns of the coil is 40 multiplied by the area, that is 4 into 10 raised to minus 4. The entire answer comes out to be 1 Weber meter square minus square meter square inverse. Okay, so your correct option is option number B. A coil of area 0.4 meter square has 100 tons. A magnetic field of 0.04 Weber per meter square inverse is acting normal to the coil surface. If this magnetic field is reduced to 0 in 0.01 seconds, then the induced EMF in the coil is. Options are 160 volt, 250 volts, 270 volts, or 320 volts. Here we are given A, which is equals to the area, that is 0.4 meter square. Then we have given the N, that is the 100 turns. Then we have given the change in the magnetic field, that is 0.04, and then we have given the time, that is 0.01 seconds. Now we know that the magnetic flux, that the induced EMF E, which is equals to the change in the magnetic flux upon time, where the magnetic flux is nothing but NA, and the change in the magnetic field upon time, so dB upon dt. So if we place all the values, we get 100 multiplied by the area, that is 0.4, into change in the magnetic field, that is 0.04 upon 0.01. So the entire answer comes out to be 160 volt, whereas A is the correct option. Okay. Next sum, a coil of mean 500 centimeter square and having 1000 turns is held perpendicular to the uniform field of 0.4 Gauss. The coil is turned through 180 degrees in 1 upon 10 seconds. The average induced EMF is 0.02 volts, 0.04 volt, 1.4 volts, or 0.08 volts. Okay, so here we have the given the things, that is area, which is equals to, again it is 500 centimeter square, so that means 500 10 raised to minus 4 meter square. Then it is having tons, that is n, which is equals to 1000 tons. Okay, then it is placed perpendicular the magnetic field to about 0.4 Gauss, which is about 0.4 into 10 raised to minus 4 Tesla. Okay, next we have given the coil is turned through 180 degrees in 1 upon 10 seconds, and the average induced EMF is, so the induced EMF is changed from average 0 degree to 180 degree. So there are two fluxes. So when the coil is held perpendicular to the field, the normal to the plane of the coil, it makes an angle 0 degree to the field B. Okay, so we have two fluxes, that is phi 1 at cos theta of cos 0 degree. So we have the formula BA cos 0 degree, that becomes BA, and phi 2 which is at BA cos 180 degree, that is equals to minus BA. Okay, so plus BA and minus BA. So the average induced EMF E, which is equals to minus of N minus BA minus of minus BA upon, that is phi 2 minus phi 1 upon the time t. Okay, so that is, it is going to be 2n ab upon time t. So we substitute the values, 2 multiplied by n, that is about 1000, multiplied by the area, that is 500 into 10 raised to minus 4, into b, that is 0.4 into 10 raised to minus 4 upon the time t. The time t gives out to be 1 upon 10th of a second, so that is 1 upon 10th of a second. So again solving this entire thing, the answer comes out to be 0.04 volts. So your correct option is B, 0.04. Okay, the next sum, an air core solenoid with a length of 20 centimeter, area of cross section 20 centimeter square, and number of turns 400, carries a current of 2 amperes. The current is suddenly switched off within 10 raised to minus 3 seconds. The average back EMF induced across the ends of the open switch in the circuit is, ignore the variation in the magnetic field near the ends of the solenoid. Okay, so the options are 2 volts, 4 volts, 3 volts, and 5 volts. Okay, so what we have given here is, we have the length L, which is 20 centimeters, that comes out to be 20 into 10 raised to minus 2 meters. Okay, next we have given the area A, which is equals to how much, 20 centimeters square, that is again 20 into 10 raised to minus 4 meters square. Next we have the number of tons N, that is 400 tons. Okay, next we have the current. The current is, there are two currents. Firstly the current I1 is 2 amps, and then the current suddenly goes to I2, that is 0. It has been switched off within a time t, that is about 10 raised to minus 3 seconds. So we need to find the induced EMFs. For the induced EMF E gives you the change in the flux upon the time. So where the change in the flux is, where the time t, where the change in the flux is given by this d upon dt of b n a n, that is the magnetic field multiplied by the area multiplied by the number of turns, where the magnetic field B is nothing but mu naught n I upon L upon the length. So we substitute the values of that B over here, we get mu naught n I a n upon, so that becomes upon L dt. Okay, so substituting all the values, we substituting the values, but here the change in the I, that is di, that is from right from 2 amps to 0 amps. So we have a change in the I, so we take mu naught n I2 minus I1, okay, into n a n, that will be n square, we'll take it later on, dt. Okay, now we substitute the values as per the rules, that is mu naught is 4 pi into 10 raised to minus 7 into the n ka square, n is the number of turns, that is 400, so that becomes 400 square multiplied by I2 minus I1, that is 2 minus 0, that becomes 2 amps, multiplied by the area is given out to be 20 into 10 raised to minus 4, so 20 into 10 raised to minus 4 upon this entire thing becomes upon the length L, that is about 20 into 10 raised to minus 2 into the change in the time, that is 10 raised to minus 3 seconds. Okay, so the overall value of this comes out to be 4 volts, so B is the correct option, 4 volts. As a result of the change in the magnetic flux linked with the to the closed loop shown in the figure, this is the diagram drawn. An EMF V volt is induced in the loop, and the work done in the joules in taking the charge Q coulomb once along the loop is. So we have to check a charge Q once along the loop in this induced EMF. Okay, so whatever the work will be done will be nothing but the amount of charge we are taking along the loop multiplied by the voltage which is being induced. Okay, so that will be nothing but Q, that is the charge we need to take along the loop multiplied by the voltage induced V. So the amount of work done will be Q into V, so option is the correct option. The next sum, two identical coaxial coils P and Q carrying equal amount of current in the same directions are brought nearer. The current in P increases while Q decreases, Q increases while P decreases. Both P and Q will increase or both P and Q will decrease. So we have two coils out here, P and Q, and they have been brought nearer, and they are carrying equal amount of current in the same direction and are brought nearer. Okay, so when such two coils P and Q are brought nearer, the magnetic flux which is linked with them, with each of the coil, will increase. Okay, and as a result the magnetic flux will increase, the induced current will try to decrease, and the flux and hence the current in both the P and Q will also, they both of them will go on decreasing when this both of the coils are tried to be brought nearer to each other. Okay, so the correct option here is D, that both the P and Q will the current in both the P and Q coils will decrease. Okay, next sum, a conducting loop is placed in a uniform magnetic field with its plane perpendicular to the field, and EMF is induced in the loop if it is rotated in its axis, it is rotated about a diameter, it is not moved, it is given translation motion in the field. Okay, so we have a conducting loop placed in a uniform magnetic field with its plane perpendicular, and we need to induce a current in it. So in order to induce an EMF inside this, the magnetic flux should change. Okay, with the loop should change, and for the loop and for the magnetic flux to in the loop to change, the loop must be in motion, and for that the loop should be rotated about a diameter. Okay, so here the correct option is B, it should be rotated about a diameter. Faraday's laws are the consequences of the conservation of charge, energy, magnetic field, both B and C, both energy and charge. Faraday's laws basically deals with the conservation of energy. Okay, not charge, not neither magnetic field. They deal with the conservation of energy. So B is the correct option. The direction of the current induced in a wire moving in a magnetic field is found using Fleming's left hand rule, Fleming's right hand rule, Ampere's rule, or right hand collapse rule. Okay, so we have this Fleming's the direction of the current induced in a wire is given by the Fleming's right hand rule. The right hand rule which states that there are three different directions for three different positions of the induced current. So we have this, if the thumb points out the motion of the conductor, then and the first finger gives you the direction of the magnetic field, then the induced EMF will be given by the second finger, by the middle finger, that is the induced EMF. Okay, so it has been given by the Fleming's right hand rule. Okay, next question. Lenz's law is a consequence of the law of conservation of charge, energy, induced EMF, or induced current. The Lenz's law, which is E equals to minus of d phi by dt, that is the induced EMF is equals to the change in the magnetic flux upon time, which opposes the which because of the opposition of the magnetic flux, we have a minus sign out here. It deals with the conservation of energy, neither charge nor nor the EMF nor the currents. It deals with the conservation of energy. A solenoid is connected to a battery so that a steady current flows through it. If an iron core is inserted into the solenoid, the current will increase, decrease, or remains the same, or first increases and then decreases. Basically, if we have a solenoid, okay, and we insert an iron core inside it, the currents inside the solenoid will decrease. This is because just inserting an iron core inside the solenoid, the magnetic flux, the magnetic field inside it will increase, and hence the magnetic flux links are linked with it, it will also increase. And as per Lenz's law, we have that whenever the EMF is induced inside the in the solenoid, in this EMF induced inside this solenoid, it will try to oppose this increase. Whatever the increase has happened, it will oppose it, and that can be achieved only and only by decreasing the current. So as a result, the current inside it will be decreased. The variation of induced EMF E with the time t in a coil in a short bar magnet is moved along its axis with a constant velocity is best represented by. So we have a variation of in the induced EMF with respect to the time whenever a bar magnet is moved along a coil. So here whenever the coil will whenever the magnet enters the coil, the magnet or whenever the magnet leaves the coil, the what happens is the polarity changes, and there will be two times opposite polarities whenever it is entering the coil or whenever it is leaving the coil. So the option B, the graph will be having showing opposite directions of the polarity, it is the correct option. When a wire loop is rotated in a magnetic field, the direction of the induced EMF changes in every 1 revolution, half revolution, 1/4 revolution, or 2 revolution. So whenever when a wire loop is rotated in a magnetic field, the induced EMF, it get reversed in every half of the rotation. Okay, so not one, not 1/4, or not two rotation revolutions. It changes in half revolutions. Okay, so correct option is half. A jet plane is traveling west at a speed of 1600 kilometers per hour. The voltage difference developed between the ends of the wings have a span of 20 meters. Uh, if the Earth's magnetic field at the location has a magnitude of 5 into 10 raised to minus 4 Tesla, the dip angle is 30 degree, and then we need to find the voltage difference. Okay, it is found to be 4.1, 2.2, 3.2, or 3.8. So here the things given are for a speed velocity which is equals to 1600 kilometers per hour. Converting into meters per second, we get at 1600 into 5 upon 18, so that gives you 444 meter per second. Okay, next thing we have is the length. Okay, so the length L is given out to be 20 meters. Next is the magnetic field, that is 5 into 10 raised to minus 4 Tesla, and next is the dip angle delta, that is 30 degrees. Okay, and then we need to find the voltage. We need to find the voltage, that is E, which is equals to BLV, where instead of B we'll take VLV, where V is the vertical component of the Earth's field. So here this V is equals to B sine theta, B sine delta we can say, so which is equals to B sine of delta into L into V. Okay, so substituting all the values, we get 5 into 10 raised to minus 4 multiplied by sine of this delta is again 30 degree, multiplied by the length, that is 20 meters, multiplied by the V, that is the voltage, that is 444. Okay, and substituting all the values, we get the value of entire value to be 2.2 volt. Okay, so B is the correct option. A 2-meter long metallic rod rotates with an angular frequency of 200 radians per second about an axis normal to the rod, passing through its one end. The other end of the rod is in contact with the circular metallic ring. A constant magnetic field of 0.5 Tesla parallel to the axis everywhere. The EMF developed between the center and the ring is, so it is the EMF generated is 100 volt, 200 volt, 300 volt, or 400 volt. So we have a metallic rod which is rotating with some angular frequency. So the length of the metallic rod is 2 meters. Okay, next it is rotating with angular frequency omega, that is 200 radians per second, and it is rotating about an axis normal to the rod, passing through it to its other end. So the other end of the rod is in the contact with the circular ring, and the constant with the constant magnetic field B, which is equals to 0.5 Tesla. Okay, so we need to find the EMF induced between the ring and the center. So that is given by E, which is equals to half of BL square omega. Okay, so half multiplied by the b, that is equals to 0.5 multiplied by L square, that is 2 square, multiplied by omega, that is 200 upon okay, that's it, upon 2. So that gives you entirely the answer to be 200 volts. Okay, so B is the correct option out here, 200 volts. We have a rectangular loop of side 6 centimeters and 2 centimeters with a small cut is moving outwards a region of uniform magnetic field of magnitude 0.4 Tesla, directed normal towards the loop. The voltage developed across the cut, if voltage of the loop is 2 centimeters per second in a direction normal to the longer side is. Okay, so we need to find the voltage developed in the small cut. So basically what we have here is a small rectangular loop out here with 6 centimeters and 2 centimeters. Okay, and there is a cut out here and we need to find the voltage developed across that cut. Okay, so the given thing here is the length of this, which is equals to solution, which is equals to 6 centimeter, that is 6 into 10 raised to minus 2 meters. Okay, next thing we have given the magnetic field, that is about 0.4 Tesla. Okay, next thing given is the voltage, which is equals to the velocity of the loop, which is 2 centimeters per second, which is equals to in meters per second, that will be 2 into 10 raised to minus 2 meters per second. Okay, so the voltage developed out here, voltage will be given by B into L into V in its velocity, that is 0.4 multiplied by 6 into 10 raised to minus 2 multiplied by the velocity, that is 2 into 10 raised to minus 2. So the entire answer comes out to be 4.8 into 10 raised to minus 4. Okay, that is the voltage developed. So correct option is B, 4.8 into 10 raised to minus 4. Okay, next sum. A metallic rod of 1 meter length is rotated with a frequency of 50 revolutions per second with one end hinge at the center and the other end at the circumference of the circular metallic ring of radius 1 meter about an axis passing through the center and perpendicular to the plane of the ring. A constant uniform magnetic field of 1 Tesla parallel to the axis is present everywhere. The EMF between the center and the metallic ring is 157 volt, 117 volt, 127 volts or 137 volts. Okay, so we need to find the EMF between the metallic ring and its center. Okay, so we are given the length of the rod, that is equals to 1 meter, and next we have the frequency n, which is about 50 revolutions per minute per second. Okay, next we have the magnetic field given, that is about B, which is equals to 1 Tesla. Okay, 1t. Next we will find the velocity. So velocity is equals to 2 pi n with respect to the frequency, so that is 2 pi into 50, so that gives you 100 into 314, that is that will be the angular velocity omega, right? So angular velocity omega is equals to 200 and 314 meters per second, sorry, the 314 revolutions per second. And next will be this the formula which we are using for the change in the for the EMF induced is given by half B L square omega. Okay, so half multiplied by this B, which is given to be 1 Tesla, multiplied by the length, that is 1 meters square, multiplied by the omega, that is 314. Okay, so we get nothing but 314 upon 2, that gives you 157 volt. Okay, so the correct option is A, 157 volts. A circular copper disc of 10 centimeter in diameter rotates at 1800 revolutions per minute about an axis through its center and at the right angles to the disk. A uniform field of induction of B of 1 Weber per meter square is perpendicular to the disk. What is the potential difference developed between the axis of the disk and the ring? Okay, the options are 0.03 volts, 23 volts, 0.23 volts, 23 volts or 230 volts. Okay, so we'll find the answer. Here for this copper disc, we have a length of the copper disc, we have the diameter, that is in diameter, rotates with the speed of 1800 revolutions per second. So here we'll find its angular velocity, that is equals to 2 pi into the frequency, that is 2 pi n, that is equals to 1800 revolutions per minute, will make it as to seconds, that is 2 pi 1800 upon 60, so that becomes 60 pi radians per second. Okay, next here we have given the length, that is equals to the radius of the disc. Okay, and the radius here, the dia is 10, so the radius will be 5 centimeters, so that becomes 5 into 10 raised to minus 2 meters. Okay, next we have given the magnetic field, uniform magnetic field B of about 1 Weber per meter square. Okay, next we need to find the E, that is again we have the formula half B L square omega. So half multiplied by B was 1, L is 5 into 10 raised to minus 2 square multiplied by the omega, that is about 60 pi. Okay, so the correct option, the overall answer comes out to be 0.23 volt. So the correct option is B, 0.23 volt. Induction furnace makes use of dash, that is the self-induction, mutual induction, eddy current, or none of this. The induction furnace doesn't works on the self-induction or mutual induction. It uses the eddy current. Okay, so C, eddy current is the correct option. Okay, the next sum. Two coils A and B are separated by a certain distance. If the current of 4 amperes flowing through A, magnetic flux of 10 raised to minus 3 Weber passes through B. So no current through B. If the no current passes through A and the current of 2 amperes passes through B, then the flux through A is. So ultimately we need to find the flux through B. The options are 5 into 10 raised to minus 3 Weber, 4 into 10 raised to minus 4, 5 into 10 raised to minus 4, or 2 into 10 raised to minus 3. Okay, so firstly, we'll find the magnetic field, magnetic flux linked with the coil. Okay, that is the M, and what we are given is the magnetic flux linked, magnetic flux with the B, and which is about 10 raised to minus 3 Weber. Magnetic flux of 10 raised to minus 3 passes through B. Then the current I through A, that is A is equals to 4 amps. Okay, so we have the formula, magnetic flux is equals to M into IA. So your M value becomes M equals to phi of B upon I of A, which is equals to 10 raised to minus 3 upon 4 Henry. Okay, next thing, the magnetic flux through A. We are going to find the magnetic flux through A, that is the flux through A. Again, using the same formula, we will be having M into IB, which is equals to M, that we found out, 10 raised to minus 3 Henry upon 4 into IB. So here the IB is equals to 2. The current passing through of 2 amp passes through B, so the current is 2, and solving this, here comes the value of 5 into 10 raised to minus 4 Weber. Okay, so the correct option is C, 5 into 10 raised to minus 4. Okay, the equivalent inductance between A and B is, through A and through B, the equivalent inductance will be, so if we draw this diagram here, they show that this and this both are parallel, this and this both are parallel, all the inductance are connected in parallel to each other. So if we draw a diagram of those inductance, we can connect them in parallel, just like the series we have inductance in parallel now. Okay, and all of them are about 4 henries. Okay, so 4 we'll use the same formula as we use for the resistance in parallel, that is 1 upon the total inductance L is equals to, across A and B, is equals to 1 upon 4 plus 1 upon 4 plus 1 upon 4 plus 1 upon 4, that gives you 4 upon 4, that is equals to 1. So 1H will be the answer, that is option number A, 1. Okay. A conducting wire of 100 turns is wound over 1 centimeter near the center of a solenoid of 100 centimeter length and 2 centimeter radius, having 1000 turns. The mutual inductance of the two coils is, so we have a solenoid which is having about N1, which is equals to 1000 turns. We have two coils, so we'll take solenoid as the N1. The length given is 100 centimeters, that is 1 meter. And next thing is, we need to find the area of this, that is pi r square. So pi becomes 3.14, and that is, we'll substitute the pi later on, that is 2. The radius given is 2 centimeters, so 2 into 10 raised to minus 2 ka square. So again we have given the turns of the second coil, that is N2, that is 100 turns. Okay, and so we need to find the mutual inductance of the two coils. The mutual inductance M between the two coils is given by the mu naught upon N1 N2 A upon L. Okay, so which will be mu naught is equals to 4 pi into 10 raised to minus 7, 10 raised to minus 7 into n1 and 2, both of them, that is 1000 multiplied by 100 into this area, that is 2, that is 2 2s are 4, that becomes 4 into 10 raised to minus 4 into pi upon the length is given out to be 1, the length is given out to be 1 meters. Okay, on solving all this we get the value of 1.58 into 10 raised to minus 4 volt. Okay, so here the correct option is 1.58 into 10 raised to minus 4. A is the correct. The equivalent inductance of two inductors is 2.4 Henry, and when they connected in parallel it becomes 10, and when connected in parallel, and 10 Henry when connected in series. What is the value of each inductance of the individual inductance, so that the of the individual inductors? Okay, so we need to find the value of each individual inductor. So let we have two inductors, that is L1 and L2. When they are connected in series, we have L1 plus L2 equals to 10 Henry. Okay, and when they are connected in parallel, we have L1 L2 upon L1 plus L2, which is equals to 2.4. So what we'll do is we'll substitute the value of L1 plus L2 in this equation. So L1 plus L2 becomes L1 L2 upon 10 is equals to 2.4. So that will be again 2.4 multiplied by 10, that becomes 10. L1 L2 equals to 24. Okay, so here we have L1 minus L2 square equals to L1 plus L2 square. We'll use the formula, that is L1 minus L2 the whole square equals to L1 plus L2 the whole square minus 4 times of L1 L2. Okay, so L1 minus L2 is equals to this L1 plus L2 is again equals to 10 ka square. Okay, so that becomes 10 square minus 4 times L1 L2 is 24. Okay, so this becomes to overall to be 2h. Okay, that is L1 minus L2 is equals to 2h. On solving this equation and this and the first equation, that is this one, L1 plus L2 equals to 10 Henry and L1 minus L2 equals to 2 Henry, we can solve them, that is adding an L2, L2 gets cancelled, the value of L1 will be equals to 6 Henry. Again, if we substitute this L1 in any of these other two equations, we'll get the value of L2, that is equals to 4 Henries. Okay, so the values are 6 and 4, that is the P is the correct option.